Time for a pop quiz. Huh, nicely integrated.
Welcome in, Zach. Happy Saturday morning to you. I suppose you're probably getting ready for your stream too, right? Hi, Martin. Welcome in. Hi, Joe. Hey, Seth. Larson, hello. Welcome in, everyone. We're just on the countdown. We're getting ready for some topology this morning, which is super exciting. In case you're in ads, I'll send a welcome message via chat too, just in case you're in an ad. But yeah, today's a big day. We got special guest Slender coming in to talk about topology of the real number line, which is pretty cool. I'm excited. Topology, Penn's favorite stop. You should have seen me looking at some of these proofs, Zach. I was like, what's going on? Why are there so many balls? I was trying to keep track of my balls, chat. I feel like topology is everyone's nemesis, Joe. Not just yours. It was definitely my nemesis when I was an undergrad. So many balls in topology, it's crazy. You got a bigger problem than just some balls? Are you just bouncing around? Oh my gosh! I wish I had speaker.bot on for that one. Oh my gosh!
Come on, Jeffrey, you can do it. Pave the way, put your back into it. Tell us why, show us how. Look at where you came from, look at you now.
Good morning, Jeff. How are you doing?
Why did you even rope me into this? Because he roped me into this. Well, him over there, he roped me into this. Well, he roped me into this.
I'm not a doctor, but I appreciate the sentiment. Doctor, I know. I'm not a doctor. I love topology, all the mountains and stuff. Oh. I'll accept that. I'll accept that this morning. Remember, 2 masters equals 1 PhD. True. True. I like that math. Okay. Yeah, that was a good one-liner. I appreciated that one a lot. All right, we are through our ad roll, so we should be just about ready to get this party started. What does 3 MSMA degrees equal? Ooh, I don't know. What do you think, chat? Can you share a PhD? Is a PhD like cake? Can you just chop it up into smaller pieces and distribute it? Alrighty, so I'm gonna go ahead and Discord and just get the party started here. Let's go ahead and start that event. Boop. Hi, Zythan. Hi, Sasha. Hope you're all doing well. Happy Saturday to you. Welcome in, everyone. My name is Penn Center. We'll give everyone a few moments to just pop into the lecture room here. We're going to be doing a presentation today on the topology of the real number line with a very special guest. You know them as Slender, but they've doxed themselves in their title slide. Alright, I don't want to wait too long, but this is one of the presentation series inside of our real analysis reading group. If you would like access to those channels in the Mandelbrot Mathematics server, please feel free to send me a DM, and I would be happy to open up those channels for you. And there will be a special, I guess, announcement at the end. Zyphon and Slender have been hard at work organizing a topology reading group for us as well. So there'll be a little bit more information about that closer to the end of the presentation. And they can let you know the easiest ways to get set up and ready for that. So without further ado, I'm going to pass the floor over to Rafid or Slender, and you are welcome to start whenever you would like, my friend.
Hello everyone, I'm Slender. My name is Rafid. Today I'll be presenting the topic on topology of the real line. So let's get into it. So here is an overview of what we are going to cover. First we will cover the open balls, then the open sets, and some theorems. Then we will cover limit points, closed sets, compact sets, and the Eine-Borel theorem, and lastly the connected sets. So let's get right into it. So firstly we will start with a review on the intervals in the real line. So the first interval, we have the open interval. This is the set of all points between A and B that doesn't include A or B. And then we have the closed interval, which is the set of all points between A and B, including A and B. And then we have the half open intervals. These are like half open and half closed, as you can see here. Now we can use this notion of open intervals and generalize it to get open sets. So for that we will need the open ball. So the open ball is defined as this open interval, that is the set of all points with distance less than r. So then we say the open ball centered at x with radius r is this. We call this a ball because it is the set of points that are close to the center x. Also, when extending to higher dimensions like 2D or 3D, it looks like a ball or a circle. Observe, now you can see that this interval excludes the boundary points x minus r and the x plus r. So this is the open interval. Now this ball is also called the neighborhood of x with radius r. Typically they use epsilon instead of r. So you can also call this an epsilon neighborhood of x. Now we will define the definition of an open set. A subset S in R is called open if for every point in x there exists a open ball centered at x with radius r that is fully contained in x. So for example, if you have this interval, that is the open interval a to b, and you take some point x here, if you draw a ball like the neighborhood of this point, that is the open ball with radius r, no matter where you draw it, it will always stay contained inside that set. So in the first example, we have the open interval, and then we have the union of two open intervals that is also open. The set of real numbers is also open. Now there is these non-examples we have. We have the closed interval that is not open because it includes the points on the boundary. So let's look at some proofs of it. So let me draw it again, the line. Here we have the open interval. We pick some point x. It doesn't have to be in the middle, it can be anywhere. This is the point x. And now this distance is x minus a, and then this distance is b minus x. So now if we consider a ball centered at x, then we can choose the radius as the smallest distance of these two. So we use min x minus a and then b minus x. We choose the minimum of these two distances. So this will make sure that this ball always stays inside this set. making this set open. So now the next example we have is R is open. So if you choose any x in R, literally any x, and then any radius, it will always have the ball contained inside R. It will always be in R, no matter where. Because if this is the real line, any point x, and you have the ball with radius R, it will always be inside R. And then we have the closed interval. This is not open. Because if you consider the closed interval a to b and consider the x at a, so we consider this point. Let me mark it with another color. We consider this point, and if we draw a ball with a positive radius, you can see this doesn't stay inside the set. It crosses the set and goes outside. So there is no choice of positive radius r that can keep the ball inside this set. So this set is not open, the closed interval. So now we have some important properties of open sets, that is the arbitrary union of open sets is open. We have we have some set Si, that is some collection of sets. Then we pick any x in the union of this collection. Then we have some Sj, x in some xj for some j inside this union. Since Sj is open, there is some ball that is contained inside Sj. Since Sj is contained in the original union of the collection of unions, it follows that the ball is contained in the Si, the union of this first collection. So the union of open sets are open. So now we have the finite intersection of open sets. So we consider the finite intersections because the arbitrary, if we take an infinite intersection, it doesn't necessarily result in an open set. So an example is, for example, we have the set Sn is equal to, say, the open interval -1 by n to 1 by n. If we consider the infinite intersection of this, starting from n equal 1 to infinity of Sn, if we consider the infinite intersection, then we will have the singleton set 0. So because this is the only common element in all of this intersection of the open intervals, so this is not open. So that's why we consider the finite intersection. So now let's go to the proof of it. So let S1 through Sn be finitely many open sets. Suppose we have some x in the finite intersection of this collection. Then since this is the intersection, this x is contained in all of these. This x belongs to all of these Si's for all I, because we have all elements common. Since each Si is open, there is some ball with radius Ri centered at x that is contained in Si. So now we choose the smallest radius, because as we take the intersections, the set becomes smaller, and so we consider the smallest radius of all these radius R1 through Rn. Then the ball with this radius stays inside Si for all I. So the intersection of open sets is open. So now the question is the empty set open? The answer is yes. Because by definition, for every point x in the empty set, there exists an open ball with radius r centered at x that is contained in this empty set. Since there are no points in the empty set, this statement is vacuously true. So it means that since our statement says that for every point x in the empty set, we don't have any points. So this statement is automatically true because there are no points to consider. So the empty set is open. We can also define it that way for it to be open. So with the open sets done, now we can move on to limit points. A point A in R is a limit point of a set if, regardless of how small you make the open ball, the set without excluding the point A always contains at least one point of S. So what does this mean? So if we look at the example here and consider this interval 0 to 1, if we consider this open interval, we can pick any point here, and no matter how small we make the ball with radius, no matter how small we make the radius, the ball will always contain at least one point of S. So yeah, so consider this point X here, or even on this very close to this 0 here, which is not included in the set. We can always draw a very small ball that will be in the set. So since we can do this in the 0 here, we can say 0 is a limit point. We can say 0 is a limit point because there are points very close to 0 that are not exactly at 0. So 0 is a limit point. Now let's look at a non-example of what's not a limit point. So consider this finite set that has 2, 4, and 6. For any point x in this set, there is no open ball with the positive radius that remains entirely within S. For example, if we take the ball centered at 2 for some r greater than 0, the set excluding that point contains no other points of S. This set is empty. This is empty. This is empty. And it doesn't contain at least one point of this set. So this is, you cannot find any limit point here. So this set contains no limit points. So we can have a theorem to help us classify limit points. So basically, if you have a set and then there is a sequence inside that set that converges to some x, but that x is not in the set. So you get close to x, but that x is not in the set. So the first example we can see here is x equals 0, as I showed earlier here, because the limit x equals 0 is a limit point since this sequence, this specific sequence, converges to 0. This sequence has terms inside this set, but it converges to 0 and 0 is not included in the set. It approaches 0, like very close, but not exactly. Now the second example is also similar. We don't have any 0 in this set. This set doesn't have any 0, but it approaches 0, any sequence in this set. So x equals 0 is also a limit point, but 0 is not in this set. And then this set 1, 2, 3, there are no limit points. There's no sequence that inside that accumulates outside S. So that means like all of this sequence are in this set. Like previous examples, we had 0 as the limit point, but 0 is not in the set. But in here we have all of these points that are in the set. So there are no limit points. So we can prove the theorem now. This proof a little bit catchy. So we'll first prove the forward direction of this proof. By definition, every open ball with radius r centered at x contains a point of S other than x itself. So as in the definition, we have the ball. So consider this is an open interval or something. This ball contains a point that is not in S. This ball has points, at least one point of S in it. Like, let me rephrase it. This ball has at least one point of S other than x itself. Here if it's x. So to prove it, we can choose this r for each balls because this is convenient to choose it. You can also use any type of sequence like 1 by n square, for example. That will be completely fine. We just chose this because it converges to 0 and it's more convenient. So for each natural number n, let Rn equals to 1 by n. Then there is some n in this intersection, that is the ball's in this set, the balls with radius Rn, that doesn't converge to x, because we are considering all the points excluding x. So we have some arbitrary r. So this now here from here is just the convergence of sequences stuff. So we choose any arbitrary r, and we have an n such that this number stays less than r. So the sequence, as you can follow, the sequence satisfies if the sequence approaches x, I mean converges to x, but x is not in this set. So this can be seen as the ball at n equals to 1 starts like this, then slowly, if this is the set, slowly gets smaller in this point x, it gets smaller and smaller, and the sequence terms in this set will also get smaller. So this sequence eventually converges to some value. Now for the backward direction, we assume there is a sequence in S such that it converges to X, and the X is not in this sequence for all n. So this is just reversing this proof. So this is just reversing. So since this sequence converges, we have for any r there is some big n such that small n greater than big N implies n minus x is less than r. So this point here, this is just the definition of the ball itself. If you look carefully, this is just ball center at x. Now we are just considering, actually it's not a ball, it's just the distance, sorry about that. It's not the ball. But as you can see, the set of all points, eventually after some radius, this sequence stays completely within a distance of r. So we take this radius and we can say this ball is in this set. So n is in this intersection for all little n bigger than greater n, showing that x is the limit point of S. So now we can go to the definition of closed sets. A set S in R is closed if every convergent sequence of points in S converges to a point in S. So if we have a set S and we have some sequences in it, let me show a different color. Let's say this is the sequence and it converges to some points. And let me show the boundaries of this set. If we have some random sequence in this set, or actually for all sequence in this set, we can have a subsequence. Actually, no, my bad. Okay, so every sequence will converge to a point inside this set. So even on the points on the boundary. So this means the set is closed if every convergent sequence of points converges to a point in S. So we can restatement it in a more formal way. S is closed if whenever a sequence xk in S satisfies the converges to A, then A is in S. So if every sequence converges to a point in S, S is closed. For example, we can consider the open interval 0 to 1, and we can choose xk is equal to 1 by k, which has terms inside this set. The sequence converges to 0, which is not in S. So S is not closed. We can have a theorem to help us determine whether a set is closed. So the theorem says that a set is closed if and only if its complement, meaning R take away S, is open. So for the forward direction, we assume that S is closed. Let X be in this complement, then X is not contained in X because we removed S. So X is not in this set S. So X is not a limit point of X, meaning we don't have X in this set. The sequences don't converge to X. So there is some open ball centered at X, inside this, because wait, just a second. Okay, so x is not a limit point of s, so there exists an open ball centered at x that is completely contained inside this complement, making this complement open. So now let's assume the complement is open. If S is not closed, there exists a limit point in S. So it's not closed. So there is some limit point, we have some limit point that is not in S. Then every open ball intersects S, contradicting that our takeaway is open. So S must be closed. So what this basically means that if this complement is open, suppose this is a real line and this is our set up till here, this is S, this is the set S. Now if S is not closed, meaning there are no sequences that converge to a point in S. So there is a limit point. Since it's not closed, meaning the sequences don't converge to a point in S. Let me use a different color. So there are sequences in this set that, for example, lie in here, and it doesn't converge to a limit point, meaning it doesn't converge to some point in S. So there are no limit points inside S, but it can be outside since the sequence is not closed. Then if we have the limit point A here, A, the open ball centered at A, intersects S. The open ball, since it has a positive radius, it will always get inside S. So our takeaway is not open. I mean, did I make a mistake here? Okay, wait, our takeaway is open. This is open. So S must be closed. Okay, this is basically what happened here. If let me mark it with another color. Suppose this blue color, this blue, the blue one is our takeaway S. So if it's open, we can always find a ball centered around it. For any X in here, we can always have a ball centered at X that is contained in here. But in here we have as you can see in the green color, in the green you can see this point A that lies on the complement. This intersects with S. This has some points in S. So this ball is not contained entirely in this complement. So we have a contradiction. So S must be closed. So now let's look at some examples of closed sets. So the closed interval is closed because the complement is open. Now, if we see the real line is also closed because its complement phi is open. So in here we can see that real line is both closed and open. Both closed and open. So we can see some non-example now. So an open interval, any open interval is not closed because the complement is not open. So does a set always have to be either open or closed? The answer is not necessarily. A set can be neither open nor closed. It can also be both. As from previous example, note that I said the complement our takeaway is this was not open. This set actually neither open nor closed. In general, the half-open intervals are neither open or closed because it's a very simple proof. For B in this set, consider the ball center at B with radius r. This ball is not contained in this set, so the set is not open. So then we can consider the sequence a plus 1 by n for a in this set. Then a approaches to an approaches to, an converges a, but a is not in this set. So this is not closed either. So any half-open intervals is neither open nor closed. So the set R and phi are, the empty set are both open and closed. So for the empty set, it becomes vacuously true that it is open. Similarly, it is vacuously true that it is closed. For R is closed because all sequences converge to a point in R. R is also open because for any point x in R, any open ball with a positive radius is contained inside X. So R is both open and closed. So now, before heading to the compact sets, we will look at we will recall bounded sets. So a set is bounded if there is a positive real number such that for any x in this set, for all x in this set, this number is always greater than the elements of x. So the set of closed interval 0 to 1 is bounded because it is bounded by 1. 1 is greater than or equal to all of the elements inside this set. Then we have R. R is not bounded because any sequence, actually the elements approach infinity. So this is not bounded. We cannot have any number bigger than this. Like we cannot have any x in R. We can't find another real number m such that x will always be less than or equal to m, because the real line is defined as this open interval. The real line is this open interval. So if you look carefully, the endpoints here, negative infinity and the infinity, these are not included in this set. And by definition, a set is bounded if there is a real number, a positive real number, such that for any element in the set, it will always be greater. But we cannot have any, we don't know what's the largest element in R, so this is not bounded. So here we come to the one of the most important part of analysis, that is compact sets. So a set is compact if every sequence has a convergent subsequence whose limit lies in S. So like the closed set definition, we now have an extra condition, that is the convergent subsequences. So all subsequences of these convergent sequences must also converge to a point in S. So this is kind of a generalization of closed and bounded sets. We will prove this in a bit. Now first let us look at some examples. The open interval 0 and to 1, this is not compact because sequences can converge to 0 or 1 which are not in S. For example, the typical sequence, that is 1 by n, this sequence converges to 0, but 0 is not in this set. So this is uncompact. So now the next example, we have this set, which is kind of weird. It looks like a sequence, but it is a set. It goes like 1, then 1 by 2, 1 by 3, and so on. But it doesn't have 0. So we union with the singleton set containing only 0. Then if we consider this same sequence in here, then this set contains 0. It has 0 in it. So since this sequence converges to 0, the subsequences also converges to 0, which we won't prove here, and I assume you all have studied that before, that every convergent sequence has a converging subsequence. Now we have a very important theorem, the Eine-Borel theorem. So a set S is compact if and only if it is closed and bounded. So a set must be closed and bounded, meaning for any x in the set, we can have a larger number that bounds the set. So we can start with the forward direction of the proof. Suppose S is compact. So since S is compact, let me write it down here. Every sequence must have a converging subsequence. So every sequence must have a converging subsequence whose limit lies in the set. So we assume S is compact, so this is assumed for S first. If S was unbounded, we could construct a sequence in S such that the sequence converges to, like, diverges. The sequence diverges. Since the sequence diverges, it cannot have a converging subsequence, so S must be bounded. So if S was not closed, there would exist a limit point, meaning if S is not closed, meaning there are no sequences that actually, not closed, meaning the sequence will not converge to a point in S. So we will be ending up with a limit point, that is, the sequence will approach X, but it won't necessarily, X won't be in the set. So a sequence Xn in S could converge to X, contradicting compactness. So S must be closed, because by compactness we should have every sequence must have a converging subsequence. So a sequence, any sequence that doesn't converge to a point in S, it will contradict the fact that S is compact. And then we have S is closed and bounded. We assume that. So S being bounded implies that all sequences in S are contained within a finite interval. So S is bounded within a finite interval, it's not infinity to infinity, something like that. So by Bolzano-Weierstrass theorem, any bounded sequence has a converging subsequence. So since this set is bounded, any sequence we find is in this set has a converging subsequence. So, and then since S is closed, the limit of this subsequence lies in X. So Bolzano-Weierstrass theorem doesn't tell us that the limit of these converging subsequences will lie in S. Doesn't tell us the limit will be in S, inside S. But then the closed, this condition is being closed, this will force upon us that the limit of this subsequence lies in the set S, because every converging sequence must have a limit point in S. I mean, must have a limit inside S, must converge to a point inside S, and there are converging subsequence because S is bounded, hence S is compact. So we are done with this very important theorem. We can now look at some examples of it. So just like before, consider this set that has 2, 4, and 6 in it. It is compact because it is closed and bounded. Now this set is bounded by 6. So 6 is a number that is greater than or less than or equal to all of this. So any sequence here is either constant or contains a converging subsequence. For example, the sequence like 2, 4, 2, 4 contains the sequences 2, 2, 2, and 4, 4, 4, and so on. These are constant. So this set is compact because any sequence has a converging subsequence. Then we can look at the union of a closed interval, a very silly example. It is compact because it is closed and bounded. It is bounded by 3. So any sequence in S stays either within one interval or has a subsequence in one interval, ensuring a converging subsequence. So if we draw it here, we know that the closed interval is closed. So this is closed. And then we again have another interval here. Now this is also closed. So the sequence converges to a point inside this. In here, the sequence also converges to a point inside it. And it is bounded by 3. So it is compact. Now, like the old example, we again have this weird set that looks like a sequence, but it's a set, it's not a sequence. That includes 0. So it is compact because it's closed and bounded. It's bounded by 1. Bounded by 1. Any sequence in here has a subsequence converging to 0. Since the main sequence in here, an is equal to 1 by n, this converges to 0, so the subsequences of this also converges to 0. So now let's look at some non-example. This is very important. The real line is not compact because it's unbounded, as we have seen before. So we can sort of visualize compact sets like this. Compact sets are closed and bounded. So this is closed. This is some closed interval which is bounded. Now non-compact set like this open interval, this is not closed and sequences may converge to points outside the S. I've been repeating this, but I will repeat again just to have some clarity. 0, but 0 is not in this interval. So you can kind of see this as some set that has sequences that behave not really nicely, like a compact set. The sequence might go outside S, which can become problematic because we work with subset of S. So now we can come to the definition of connected and disconnected. So before giving the definition of connected, we will look at what is disconnected. Then we can negate that and give the definition of connected. So a subset is disconnected if there exist two disjoint non-empty open sets A and B such that the union will give us this set. So for example, this is the set A and this is the set B. Let me mark it with some another color. This is the set B. If we union these two sets are disjoint. They don't share anything in common. So A intercept B is equal to 5. the empty set. So these are disjoint sets. And then if we union this, we will get our subset S. And remember, A and B are open. These are open. And S will also be open. So the intuition behind this is that we can split S into A and B that do not stick together. Like we can kind of take S and separate it into two pieces that are disjoint. You can kind of think it as like Play-Doh. You can think it as like Play-Doh. Let's say this line this line is some Play-Doh thing, some Play-Doh toy. You can separate it in two disjoint lines. Then this set, suppose this is the set, and we split it into A and B, then this is disconnected. So let's look at some concrete examples. So let S be the union of these two open intervals. Now we can simply choose A and B, where clearly A and B are disjoint non-empty open sets. Then A union B gives us the set. So the set S is disconnected. So now I'm going to we will cheat a bit here and say I say disconnected if it's not disconnected. This is cheating because this doesn't really help when doing the math. But let's see if we can get the definition of connectedness from this disconnected. So can we somehow negate the definition of disconnected to obtain the definition of connected? So if we remember the definition of the disconnected sets, a set is disconnected if there exist two disjoint non-empty open sets. So we will negate this entire statement. So we can come up with a better definition by negating the definition of disconnected by saying if for any two. So this changed from there exists to for any. So we negated it. So if for any two disjoint open subsets A, B with A union B implies that either A or B is empty. So if we consider our line here and we separate it into A and B, let me use some other color here. If we separate it into A and B, then either A is equal to empty or B is empty. Either one of these. So this is the definition of connected. It's like it's connected in one piece. You cannot split it into two disjoint open, non-empty open sets. So the best analogy for these disconnected sets these are Play-Doh. And connected sets, these are like maybe a metal rod, I don't know. You cannot like split it into two disjoint non-empty open sets. Obviously these are just analogies, but I hope it can help you understand. So this can be disconnected sets can be split into two disjoint non-empty sets, but connected sets they cannot be split into two disjoint non-empty sets. So here are some examples of connected sets. Any disconnected sets are not connected by the definition. Then we have R is connected. The intervals is connected. So generally any interval is connected because if you think about it, let's say this is our interval, can be open, can be closed, doesn't matter. this is connected because you cannot split it into two disjoint empty sets. For example, if you try to split this, how can you split it? You cannot have like two, this is equal to S, for example. You cannot split it into A union B that gives us S. Because if we consider the middle point, for example, 1/2, then this point is, and this is an open set, for example, open set or open interval, then we can choose A to 0 to the half. Now here is the problem here. We don't know what endpoint to use, what to use at the endpoint. Will we use the closed bracket of the parenthesis? So if we do this, these two sets are not disjoint. It's like if we do A union B, we still don't get this set. These are disjoint, but these are not disjoint, I think. So actually, yeah, these are disjoint. These are disjoint sets. So if you consider the union of this A and B, you can see that it doesn't contain that the 1/1/2. It doesn't have 1/2. It's not included in this union. So this doesn't give us our original set S. So we can now prove this very elegant proof that any interval in R is connected. So suppose for contradiction that I is disconnected. I is our interval. I forgot to mention here. So I in R is connected. And I is any interval. That was a typo, sorry about that. So suppose we will prove this by contradiction. So let's assume that I is disconnected. Then we have two disjoint non-empty sets such that I is equal to the union of these two sets. So this is I, and we can split it into U and V, U and V. So we pick some A in U and some B in V, with A is less than B. So we pick A in U and B in V. So now we consider A is equal to the big A. The big A is equal to the intersection of this. So we only consider, let me mark it with green. So let's consider only this part, which is A. This is non-empty because we have the element A inside this big A. So now we can define C as the supremum of this set, the least upper bound. So it's going to be lying somewhere around here, since this is an interval. Somewhere around here, this is C. So this is sup A. Since I is an interval, C is in I. Because C is the least upper bound of A, and A is a subset of I. And if C was not in A, it would be in I. So we must have C in the interval I. But C must be in either U or V. You can see C has to be in either U or V, because our assumption is that I is the union of U and V. So C must belong to either U or V. So this contradicts the assumption that U and V separate I. Because what just happened here is that we had this set A. We had this set A, which is just the intersection of I with U. And then we define the supremum as C, supremum of this set A as C, and we have C lying in the interval. C lies in the interval, but it must belong to either U or V. We don't know. It must be in either U or V. We don't know for sure. So since it must belong to either one of them, this contradicts the assumption that U and V separate I, because these two must be disjoint. So we should be able to find a point that is either in U or V, but we don't know. It must belong to either U or V. So it contradicts that U and V separate I. So I is not disconnected. I is connected. So the corollary of this theorem is that R is connected because R can be defined as the open interval that goes from negative infinity to infinity, which is its own subset. So it's its own interval. So this is the corollary of this proof. So now we can visualize connected versus disconnected. This is a summary. Any 2 points in S can be connected without leaving S. And disconnected set, the two pieces are separated, meaning S is disconnected. So as I said, this is Play-Doh. And this is metal rod. They cannot be separated by any means. Thank you for your time and attention. I hope you learned something. Big thanks to Zyphon and Coffee for giving me advice for this presentation. And thanks to the Mathematics Discourse server for letting me present. And thanks to Pen Center. Yeah, that was the end.
Yeah, did you want to take some time to... Do you have your slide about topology, the class that you're hoping to run with Zyphon?
By the way, me and Zyphon are hosting a topology course in the Maths Discord server. So it's not just in R, but in a more broader sense. So we will be doing topology on more abstract spaces. So maybe something like the topology of, say, as simple as ABC. How weird does that sound? We don't have open balls here or anything. So if you are interested in more topology, you can join the topology course that's being hosted at discord.gg/maths. And goodbye.
So for those of you that are still kicking around, if you want to, if you have any kind of final thoughts or questions, you're more than welcome to post them up. So Storm on Twitch made a very good point. The last theorem that we talked about, which is this idea that an interval is connected, does go backwards. So if I have an interval, I can prove that it's connected using this topological argument. And then it is also true that if I have a connected subset in R, it has to be an interval. So this kind of completely, I think, defines at least part of the topological argument on R, right? So it really helps define what these spaces look like. So yeah, thank you for that comment, Storm. And thank you very much, Slender, for the presentation. Let's see, I'm gonna go ahead, we can probably, oh, that's too big. There we go. We can probably pop out like that. Sir Roni, looks like they're typing something in Discord. I'll chill out for a second and see what they are going to type. So for those of you, next presentation will be by coffee, and we're just trying to finalize the time either next week or the next couple of weeks. So once we get that sorted out, we'll let you know. The presentation slides, Slender, if you're able to post them up in the presenters channel, I will put them under the materials for everyone, and then we'll go ahead and we'll post this VOD over to YouTube as well. So anyone that would like to go back through, because there was a lot of compact information, you know, for lack of better words here. So if you want to go back and review anything, we'll post all that up for you guys for reference. We got a Slender Rocks from Scandi.
How can a set be compact, then how can a different set be non-compact? So as I said before, a set is compact if, sorry Ronnie, if you're listening this, a set is compact if for every sequence in this set you have the converging subsequence. So it's like a generalization of being closed and bounded. So if you have a set that is both closed and bounded, compact, like if you think of it as the English word compact, it means like something can be like boxed into something. So if a set is compact if it's closed and bounded. The bounded mixture is like finitely like put in a place, and the closed mixture that any sequence inside the set doesn't go outside the set.
Yeah, so it has to contain all of its limit points then, but it also can't, in R, it can't
Yeah, exactly.
it can't go off to minus infinity or positive infinity then, right? So it has to have an upper and lower bound, is what you're saying, I think.
And all sets are bounded. Not necessarily. All closed sets are not bounded. Like the real line. The real line is closed, but it's not bounded.
Yeah, okay, yeah, that's a really good follow-up question, because I think this is helping me clarify a couple things. So yeah, you can have a closed set, but it's only compact if it's bounded then, right?
Yeah.
Yeah, so I think that's maybe what they're trying to get at, Roni, is they're trying to differentiate between sets that are closed and these kind of this subset of closed sets that also happen to have this property of being bounded.
How can a closed set be unbounded? So let me bring up my
And
So
Storm,
Ronnie, can you
yeah,
see
I'll
the
pop in here. I
thing?
I have a comment that I want to read out while you're finding the slide you want. Storm is saying compact implies any covering can be reduced to a finite subcovering, and I think that's something that you and Xiphon are definitely going to explore a little bit more in a general sense in the topology course.
Yeah. So in here we left out the definitions of open covered and subcovered things, which we will do in the topology course. Here. So how can a closed set be unbounded? So the real line is closed, but it is unbounded. Let me show. Here, as I said, the real line is closed, but it's unbounded. Here is the proof that the real line is closed because all sequences converge to a point in R. Does it answer your question, Sir Ronnie?
Yeah, so R is closed because it has to contain all of its limit points because it's
Yeah.
the universal set.
Yeah.
And Storm makes a really interesting point. He or she mentions that compact implies bounded, but the reverse is not always true. It just happens to be true in this particular dimension we're working with. Bounded and closed. Compact doesn't always imply bounded and closed, I see.
Yeah, because by the Heine-Borel theorem, we have being closed and bounded means compact. So that's one of the conditions for being compact, being closed and bounded. So compactness will imply bounded, but bounded doesn't necessarily mean the set is closed. So that doesn't directly imply that
Right.
the set is compact.
Yeah, that makes sense. And this might be why we kind of start thinking about topology over the real number line, because it does tend to be a little bit nicer to work within these more generalized spaces too.
Yeah, exactly. The definitions we see here, these all literally change when we study more abstract spaces.
All right, so I'm gonna stay open here on Discord, Slender. I'm gonna go ahead and start a raid on Twitch. We're gonna be moving over. I think Zach just went live, so I'm gonna go take care of that. But you're welcome to kind of chill out in Discord, and if Roni has some other questions, you can answer that. I'll be back in a second. Okay.
Alright, sure.
All right, everyone. Thanks for coming and hanging out this morning as we talked a little bit about the topology of the real number line. I noticed that Zach has gone live this morning, so we are going to pop a raid over to e to the 2I pi and see what Zach is up to this morning. As stated, we'll be back either next week or the week after, or maybe both, depending on what material Coffee would like to cover for his presentation, which is happening next. That's going to be on functional limits and continuity. And that's going to be happening at some point over the next coming weeks. Remember, there is no linear algebra meeting this week. We're taking the week off, so the next time we may get together will be on Sunday. I've approached Talos just to see if we can hang out on Sunday, so maybe I'll see you Sunday over on Talos's channel with regard to his exploratory calculus course. And then Zach and I are back Monday and Wednesday this coming week, 8 to 10 in the morning, doing our exploratory linear algebra class. So I'll see you soon, everyone. Have a fantastic rest of your day. Thanks, Storm, for coming in. Good to see you again, buddy. And let's go say hi to Zach. So if you want, we have a little raid message here. You can go say hi. And we'll talk to you guys soon.